Welcome to week 3 of our lecture series. Today we will explore amplitude modulation with suppressed carrier, specifically focusing on double sideband suppressed carrier, DSBSC, and single sideband suppressed carrier, SSBSC. These techniques are essential in improving the efficiency of AM transmission systems. Let's dive into the details. In our previous discussions, we learned that AM DSBFC, or double sideband full carrier, is inefficient. Why is that? Well, 2/3 of the transmitted power, or 66.67%, carries no information because it's used by the carrier. Additionally, both sidebands contain the same information, which is redundant. To address these inefficiencies, we can use two strategies. 1. Suppress the carrier, and 2. Eliminate one sideband. This leads us to two improved modulation schemes: double sideband suppressed carrier, DSBSC, and single sideband suppressed carrier, SSBSC. Let's explore these in detail. Let's start by comparing the three common AM. 1. Part A shows the modulating signal, which is the original information signal. 2. Part B represents the DSBFC wave, where both sidebands and the carrier are present. 3. Part C shows the DSBSC wave, where the carrier is suppressed but both sidebands remain. 4. Part D illustrates the SSBSC wave, where only one sideband is transmitted and the carrier is suppressed. Now the question is, how are DSBSC and SSBSC implemented? Let's find out in the next slides. Let's take a closer look at DSBFC, or double sideband full carrier. In DSBFC, the transmitted signal consists of a constant carrier and the modulating signal. If we remove the constant carrier, what happens? The carrier is suppressed, and we're left with the sidebands. Mathematically, this can be expressed as 2 cosine of 2 pi times f sub c plus f sub m times t plus mee sub c cosine of 2 pi times f sub c minus f sub m times t. In other words, the carrier is removed from the AM signal, leaving only the sidebands. This is the DSBSC. Now let's discuss the DSBSC modulator. Suppose we have a modulating signal, V sub m of t, and a carrier signal, V sub c of t. These can be expressed as V sub m of t is equal to E sub m cosine of omega sub m times t, which is also equal to E sub m cosine of 2p f sub m times t. V sub c of t is equal to cosine of omega sub c times t, which is also equal to cosine of 2 pi f sub c times t. The output of the DSBSC modulator, V sub DSBSC of t, can be written as V sub DSBSC of t is equal to me sub c divided by 2 cosine of 2 pi times f sub m times t plus me sub c divided by 2 cosine of 2 pi times f sub c plus f sub m times t. Alternatively, it can also be expressed as V sub DSBSC of t is equal to E sub m divided by 2 cosine of 2 pi times f sub c minus f sub m times t plus E sub m divided by 2 cosine of 2 pi times f sub c plus f sub m times t. This equation shows that the DSBSC signal consists of two frequency components, the lower sideband and the upper sideband. From the previous slide, we can see that the DSBSC signal, V sub DSBSC of t, is composed of two parts. 1. The upper side frequency component, and 2. The lower side frequency component. In the frequency domain, the DSBSC signal has two peaks, one at f sub c minus f sub m and another at f sub c plus f sub m. The carrier frequency, f sub c, is suppressed, meaning it's not present in the transmitted signal. Remember that E sub m is me sub c amplitude of the modulating signal, and E sub c is the amplitude of the carrier signal. This relationship is crucial in understanding the power distribution in DSBSC, which we'll discuss next. From the previous slide, we have the expression for the DSBSC signal. V sub DSBSC of t is equal to E sub m divided by 2 cosine of 2 pi times f sub c minus f sub m times t plus E sub m divided by 2 cosine of 2 pi times f sub c plus f sub m times t. This signal is produced when a carrier is modulated by a single-tone sinusoidal wave information signal. The key feature here is that the carrier signal is suppressed, leaving only the upper and lower sidebands. This type of signal is known as a reduced carrier transmission or double sideband suppressed carrier, DSBSC signal. It's more efficient than DSBFC because it doesn't waste power on the carrier. Now let's look at some important characteristics of the DSBSC, same as that of the modulating signal in DSBFC, which is a pure AM signal. Another key characteristic is the phase transition. In DSBSC, there are two adjacent positive going half cycles at the null points in the wave. This is a result of the carrier being suppressed. The DSBSC signal is created using a circuit called a balanced modulator. The functions of the balanced modulator are 1. To produce the sum and difference of the sideband frequencies, and 2. To balance out the carrier, ensuring it's suppressed in the final output. Let's now discuss the power distribution in DSBSC. In DSBSC, all the transmitted power is concentrated in the sidebands. There is no power wasted on the carrier. The total power, P sub T, is the sum of the power in the lower sideband, P sub LSB, and the upper sideband, P sub USB. Mathematically, this can be expressed as P sub T is equal to P sub LSB plus P sub USB, which is equal to V sub LSB sub USB RMS squared divided by R. If we assume the amplitude of each sideband is E sub m divided by 2, the total power can be simplified to P sub T is equal to E sub m divided by 2 square root of 2 all squared plus E sub m divided by 2 square root of 2 all squared, which is equal to E sub m squared divided by 4R. Thus the total power squared divided by 4R. Thus the total power is P sub T is equal to P sub SB, which is equal to E sub m squared divided by 4R. If we assume R is 1 ohms, the efficiency of DSBSC is 100%, meaning all the power is used to transmit the information. Let's summarize the characteristics of DSBSC. Transmission bandwidth is BO2 F sub mt, where F sub m is the frequency of the modulating signal. 2. DSBSC transmits both sidebands, USB and LSB, which contain identical information. The benefits of DSBSC are 1. No power is wasted on the carrier, making it 3 times more efficient than traditional DSBSC. However, there are also some problems. 1. DSBSC still transmits both sidebands, which is a waste of channel bandwidth. 2. It requires a fairly complicated circuitry at the receiver to avoid phase errors during demodulation, which can be expensive. To further improve upon DSBSC, we can use single sideband suppressed carrier, SSBSC. In SSBSC, only one sideband is transmitted, either the lower sideband, LSB, or the upper sideband, USB. There are 2 methods to generate SSBSC. 1. The filtering method. First, generate a DSBSC signal and then use a bandpass filter to select only one sideband, either LSB or USB. 2. The phasing method. Use an ideal which allows us to isolate one sideband. We'll explore these methods in more detail in the next slides. Let's now look at the mathematical representation of SSBSC. Suppose we have a modulating signal, V sub m of t, and a carrier signal, V sub c of t. The modulating signal can be expressed as V sub m of t is equal to E sub m cosine of 2 pi f sub m times t. The Hilbert transform of the modulating signal V sub h of t is V sub h of t is equal to E sub m cosine of 2 pi f sub m times t plus pi divided by 2, which is equal to E sub m sine of 2 pi f sub m times TL. Using these, the SSBSC signal V sub SSBSC of t can be expressed as V sub SSBSC of t is equal to E sub m divided by 2 cosine of omega sub m times t times cosine of omega sub c times t plus or minus E sub m divided by 2 sine of omega sub m times t times. The plus sign corresponds to the lower sideband, LSB, and the minus sign corresponds to the upper sideband, USB. This allows us to choose which sideband to transmit. From the previous slide, we have the expression for the SSBSC signal. V sub SBSC of t is equal to E sub m divided by 2 cosine of omega sub m times t times cosine of omega sub c times t plus or minus E sub m divided by 2 sine of omega sub m times t times sine of omega sub c times t. This can be further simplified to V sub SSBSC of t is equal to E sub m divided by 4 cosine of omega sub c minus omega sub m times t plus E sub m divided by 4 cosine of omega sub c plus omega sub m times t plus or minus E sub m divided by 4 cosine of omega sub c minus omega sub m times t minus E sub m divided by 4 cosine of omega sub c plus omega sub m times t. This equation shows that we can choose to transmit either the lower sideband, LSB. If we use the minus sign, the upper sideband, USB, is transmitted. If we use the plus sign, the lower sideband, LSB, is transmitted. This flexibility allows us to conserve bandwidth by transmitting only one sideband. Let's now look at the mathematical expressions for the lower sideband, LSB, and upper sideband, USB, in SSBSC. For the lower sideband, LSB, V sub SSB LSB of t is equal to E sub m divided by 2 cosine of omega sub c minus omega sub m times t. For the upper sideband, USB, V sub SSB USB of t is equal to E sub m divided by 2 cosine of omega sub c plus omega sub m times. SSBSC signal contains only one sideband, either LSB or USB, depending on the chosen configuration. Let's revisit the expressions for the SSBSC signals. For the lower sideband, LSB, V sub SSB LSB of t is equal to E sub m divided by 2 cosine of omega sub c minus omega sub m times t. For the upper sideband, USB, V sub SSB USB of t is equal to E sub m divided by 2 cosine of omega sub c plus omega sub m times t. What does this mean? In SSBSC, only one sideband is transmitted, which significantly reduces the bandwidth required for transmission. This makes SSBSC more efficient than DSBSC, where both sidebands are transmitted. However, SSBSC requires more complex circuitry to now let's look at the frequency spectrum of the SSBSC signal. The SSBSC signal can be expressed as V sub SSB of t is equal to E sub m divided by 2 cosine of omega sub c minus omega sub m times t, or E sub m divided by 2 cosine of omega sub c plus omega sub m times t. In the frequency domain, the SSBSC signal has two possible peaks, one at f sub c minus f sub m for the lower sideband LSB, and two at f sub c plus f sub m for the upper sideband USB. The amplitude of each sideband is E sub m divided by 2, and the carrier frequency f sub c is suppressed. This means the SSBSC signal occupies only half the bandwidth of a DSBSC signal. Let's analyze the power distribution in SSBSC. In SSBSC, the total transmitted power, P sub t, is concentrated in one sideband, either the lower sideband, LSB, or the upper sideband, USB. The power in each sideband can be expressed as P sub USB, which is equal to P sub LSB, which is equal to V sub LSB RMS squared divided by R, which is equal to E sub M squared divided by 2 square root of 2 all squared times R. Thus, the total power is P sub T is equal to E sub M squared divided by 8R. If we assume R 1 ohm, the transmitting power in SSBSC is reduced by 50% compared to DSBSC. This is because only one sideband is transmitted, making SSBSC even more efficient. Now let's move on to vestigial sideband VSB transmission. VSB is a modified AM transmission technique where 1. One sideband is fully transmitted, 2. The carrier is partially transmitted, and 3. Only a portion of the other sideband is transmitted. VSB is an efficient way of conserving bandwidth, especially for signals that have frequency content down to 0 frequency, such as video signals. VSB is generated by partially suppressing one of the sidebands using a sideband shaping filter. This technique is commonly used in television broadcasting where bandwidth conservation is critical. Let's take a closer look at vestigial sideband, a VSB transmission. In VSB, the remainder of the lower sideband is transmitted along with the upper sideband and a portion of the carrier. A classic example of VSB is in television signals. A TV picture signal has a nominal bandwidth of 4.5 MHz. If DSB modulation were used, it would require at least 9 MHz for each TV channel. However, by using VSB modulation, the entire TV signal is confined to about 6 MHz. This is achieved by 1. Transmitting the picture carrier, 2. Partially suppressing the lower sideband, and 3. Transmitting the upper sideband along with a portion of the lower sideband. This makes VSB an efficient modulation technique for broadcasting. Now let's shift our focus to AM signal generation. There are two main methods for generating AM signals. 1. The direct method, and 2. The indirect method. We'll explore both methods in detail, starting with the direct method. Let's begin with the direct method for generating DSBFC, double sideband full carrier signals. In the direct method, the modulating signal V sub m of t is directly multiplied by the carrier signal cosine of omega sub c of t. The output of the modulator, V sub am of t, can be expressed as V sub am of t is equal to E sub c times 1 plus m cosine of omega sub m times t, all multiplied by cosine of omega sub c times t. Here, E sub c is the amplitude of the carrier, m is the modulation index, and omega sub m is the angular frequency of the modulating signal. This equation shows that the AM signal consists of the carrier and the sidebands, which are generated by the modulation process. Next, let's look at the indirect method for generating DSBFC signals. In this method, a nonlinear device is used to combine the modulating signal V sub m of t and the carrier signal V sub c of t. The input signal to the nonlinear device is V sub I of t is equal to V sub m of t plus V sub c of t, which is equal to E sub m cosine of omega sub m times t plus E sub c cosine of omega sub c times t. The output of the nonlinear device V sub k of t can be expressed as V sub k of t is equal to E sub 0 plus m sub 1 times V sub I plus m sub 2 times V sub I squared, and so on. This output contains the carrier and the sidebands, which are then filtered to produce the final AM signal. Let's compare the direct and indirect methods for generating DSBFC signals. In the direct method, the AM signal is expressed as V sub AM of t is equal to E sub c times 1 plus m cosine of omega sub m times t, all multiplied by cosine of omega sub c times t. In the indirect method, the output of the nonlinear device is V sub null of t is equal to m sub 1 times E sub c times 1 plus 2 times m sub 2 divided by m sub 1 times E sub m cosine of omega sub m times t, all multiplied by cosine of omega sub c times t. What does this mean? Both methods produce an AM signal that contains the information frequency, but the amplitude of the signal varies depending on the method used. The indirect method introduces additional terms due to the non-linear device, but the final result is still an AM signal with the carrier and sidebands. Now let's discuss the generation of DSBSC, double sideband suppressed carrier, signals. Similar to DSBFC, there are two methods for generating DSBSC signals. One, the direct method, and two, the indirect method. In the direct method, a balanced modulator is used. The balanced modulator acts as a multiplier, combining the modulating signal V sub m of t and the carrier signal cosine of omega sub c times t to produce the DSBSC signal. The output of the balanced modulator, V sub DSBSC of t, can be expressed as V sub DSBSC of t is equal to V sub m of t times cosine of omega sub c times t. This equation shows that the DSBSC signal contains only the sidebands with the carrier suppressed. Let's now look at the indirect method for generating DSBSC signals. In this method, two full AM modulators are used. The input signals to these modulators have different polarities but the same carrier frequency. The output of the first AM modulator is E sub c plus 0.5 times V sub m of t times cosine of omega sub c times t. The output of the second AM modulator is E sub c minus 0.5 times V sub m of t times cosine of omega sub c times t. When these two signals are combined, the carrier components cancel out, leaving only the sidebands. This results in a DSBSC signal where the carrier is suppressed. Now let's move on to the generation of SSBSC, single sideband suppressed carrier signals. There are two main methods for generating SSBSC signals. One, the filtering method, and two, the phase shift method. In the filtering method, the process involves two steps. One, first, generate a DSBSC signal using a balanced modulator. Two, then use a bandpass filter, BPF, to select either the lower sideband, LSB, or the upper sideband, USB. This method is straightforward but requires a highly selective bandpass filter to isolate the desired sideband. Next, let's discuss the phase shift method for generating SSBSC signals. In this method, two balanced modulators are used with a 90-degree phase difference between them. The modulating signal V sub m of t is split into two components. One component is multiplied by the carrier signal cosine omega sub c times t. Two, the other component is phase shifted by 90 degrees and multiplied by the carrier signal sine omega sub c times t. The outputs of the two modulators are then combined to produce the SSBSC signal. This method avoids the need for a highly selective bandpass filter, making it more practical in some applications. From the previous slide, we can express the SSBSC signal V sub SSBSC of t as V sub SSBSC of t is equal to E sub m divided by 2 times cosine of omega sub m times t times cosine of omega sub c times t plus or minus E sub m divided by 2 times sine of omega sub m times t times sine of omega sub c times t. The plus sign corresponds to the lower sideband, LSB, and the minus sign corresponds to the upper sideband, USB. This equation shows that the SSBSC signal contains only one sideband, either LSB or USB, depending on the chosen configuration. This makes SSBSC more efficient in terms of bandwidth usage compared to DSBSC. Now let's discuss the generation of VSB, vestigial sideband signals. VSB signals are generated by suppressing one of the sidebands using a VSB filter. The modulating signal, V sub m of t, and the carrier signal, V sub c of t, are combined and pass through the VSB filter. The filter suppresses one sideband and allows the other sideband and a portion of the carrier to pass through. The output of the VSB filter is the VSB signal, which contains one fully transmitted sideband, 2, a portion of the other sideband, and 3, a portion of the carrier. This technique is commonly used in television broadcasting to conserve bandwidth. Now that we've covered the generation of AM signals, let's move on to demodulation. Demodulation is the process of extracting the original information signal from the modulated carrier wave. There are two main methods for demodulating AM signals.
1. Envelope detector, and 2. Square law detector.
We'll explore these methods in detail in the upcoming
Demodulation
slides.
is the reverse process of modulation. It converts the modulated carrier wave back into the original information signal. In other words, demodulation extracts the information-bearing signal from the modulated carrier. Focusing at the receiving end, the receiver processes the modulated signal, which may also include noise, N of t. The goal is to recover the original signal, V sub M of t, as accurately as possible. There are two main methods for demodulating AM signals. 1. Envelope detector, and 2. Square law detector. We'll explore these methods in detail in the following slides. The envelope detector is one of the most popular methods for demodulating AM signals. It's also known as a rectifier detector or diode detector. The envelope detector is popular because it's simple, low cost, and doesn't require a local carrier generator. As the name suggests, the envelope detector detects the envelope of the modulated signal, which corresponds to the original information signal. The filter used in an envelope detector is typically an RC low-pass filter, which removes the high-frequency carrier and leaves behind the low-frequency information signal. Let's look at an example of an envelope detector circuit. The circuit consists of a diode, a resistor, R, and a capacitor, C. The input to the circuit is the AM signal. V sub AM of t is equal to E sub C plus V sub M of t, all multiplied by cosine of omega sub C times t. The diode rectifies the signal, allowing only the positive half cycles to pass through. The capacitor and resistor form an RC low-pass filter, which filters out the high-frequency carrier and retains the low-frequency information signal. The output of the circuit is the demodulated signal, which corresponds to the original information signal, V sub M of t. The performance of the envelope detector depends on the time constant, RC, of the circuit. The time constant determines how quickly the capacitor discharges. Asterisk, if the RC value is too large, the capacitor discharges slowly, causing diagonal clipping. This means some parts of the signal at the peaks are not detected, leading to distortion. Asterisk, if the RC value is too small, the capacitor discharges too quickly, causing excessive ripple in the output signal. This also leads to distortion. Therefore, it's important to choose an optimal RC value to avoid these issues. To avoid diagonal clipping and excessive ripple, the rule of thumb for choosing the RC value is RC is less than or equal to 1 minus M squared, all raised to the power of 1 over 2, divided by M times omega sub M, where asterisk M is the modulation index. Asterisk omega sub M is the angular frequency of the modulating signal. This equation ensures that the RC value is chosen to balance the discharge rate of the capacitor and avoid distortion in the demodulated signal. Let's analyze the operation of the envelope detector in more detail. The diode acts as a switch that allows the capacitor to charge when the input signal is greater than the output voltage. When the input signal, S of t, is greater than the output voltage, V sub O of t, the diode, is forward biased, and the capacitor charges with a time constant. Tau sub 1 equals R sub S times C sub 1. When the input signal is less than the output voltage, the diode is reverse biased, and the capacitor discharges with a time constant. Tau sub 2 equals R sub 1 times C sub 1. This charging and discharging process allows the envelope detector to accurately recover the original information signal. Let's break down the operation of the envelope detector step by step. 1. When the input signal, S of t, is greater than the output voltage, V sub O of t, the diode is forward biased. This allows the capacitor, C sub 1, to charge with a time constant. Tau sub 1 equals R sub S times C sub 1, where tau sub 1 is way more or less than 1 over F sub C. 2. When the input signal is less than the output voltage, the diode is reverse biased and the capacitor discharges with a time constant. Tau sub 2 equals R sub 1 times C sub 1, where tau sub 2 is between 1 over F sub C and 1 over BW. This charging and discharging process ensures that the output voltage, V sub O of T, follows the envelope of the modulated signal, effectively recovering the original information signal. Let's analyze the voltage at different points in the envelope detector circuit. 1. At point A, the voltage is the modulated AM signal, E sub C plus V sub S of T, all multiplied with cosine omega sub C times T. 2. At point B, after passing through the diode, the voltage is E sub C plus V sub S of T. 3. At point C, after the RC low-pass filter, the voltage is 1 over pi times E sub C plus V sub S of T. 4. At point D, the final output voltage is 1 over pi times V sub S of T. This shows how the envelope detector extracts the original information signal, V sub S of T, from the modulated carrier. To model the diode in the envelope detector, we can represent it as a switch. The output of the diode, V sub D, can be expressed as V sub D is equal to E sub C plus V sub M of T, all multiplied by cosine of omega sub C times T, all multiplied by K of T. Here, K of T is a mathematical representation of the diode switching function. Expanding this, we get V sub D is equal to E sub C plus V sub S of T, all multiplied by cosine of omega sub C times T, all multiplied by half plus 2 over pi times cosine O omega sub C times T minus 1/3 cosine of omega sub C times T, and so on. At point B, the voltage can be simplified to V sub D is equal to 1 over pi times sum of E sub C plus V sub S of T plus higher frequencies. The higher frequencies are filtered out by the RC low-pass filter, leaving behind the original information signal. After the RC low-pass filter, the voltage at point C is V at point CC is equal to 1 over pi times E sub C plus V sub S of T. The capacitor, C, blocks the DC component, E sub C over pi, so the final output voltage at point D is V at point D is equal to 1 over pi times V sub S of T. This is the demodulated signal, which corresponds to the original information signal, V sub S of T. The envelope detector successfully extracts the information signal from the modulated carrier. Now, let's move on to the square law detector, another method for demodulating AM signals. The square law detector uses a nonlinear device, such as a diode, that follows the square law relationship. Y is equal to x squared. The AM signal is first passed through the square law device, and then through a low-pass filter, LPF, to remove the high-frequency components. The output of the square law detector is the demodulated signal, which corresponds to the original information signal. Let's analyze the operation of the square law detector. The input to the square law device is the AM signal. V sub AM of T is equal to E sub C plus V sub S of T, all multiplied by cosine of omega sub C times T. The output of the square law device is X of T is equal to V sub AM of T, all squared, which is equal to E sub C plus V sub S of T, all multiplied by cosine of omega sub C times T, all squared. Expanding this, we get X of T is equal to E sub C squared times cosine square of omega sub C times T, plus V sub S squared T times omega sub C times T plus 2 E sub C times V sub S of T times cosine squared of omega sub C times T. This can be further simplified to X of T is equal to half of E sub C squared, plus half of E sub C squared times cosine of 2 omega sub C times T, plus half of V sub S of T squared, plus half of E sub S of T squared times cosine of 2 omega sub C times T, plus E sub C times V sub S of T, plus E sub C times V sub S of T times cosine of 2 omega sub C times T. Let's rearrange the signal components from the square law detector to better understand the demodulation process. The output of the square law device x of t can be expressed as x of t is equal to 1 over 2 times e sub c squared plus e sub c times v sub s of t plus 1 over 2 times v sub s of t squared plus 1 over 2 times e sub c squared plus 1 over 2 times v sub s of t squared plus e sub c times v sub s of t, all multiplied by cosine of 2 omega sub c times t. This equation contains 1. DC components, 2. The information signal, E sub c times V sub s of t, and 3. Signal harmonics at 2 omega sub c. After passing through the capacitor to remove DC components and the low-pass filter to filter out harmonics, the final output is y of t is equal to E sub c times V sub s of t. This is the demodulated signal, which corresponds to the original information signal, V sub s of t. Congratulations! You've reached the end of week 3 of our lecture series. This week we covered 1. AM with suppressed carrier, DSBSC and SSBSC. 2. The generation and demodulation of AM signals. And 3. The envelope detector and square law detector. These concepts are fundamental to understanding how AM signals are processed and how we can improve their efficiency. Make sure to review the material and practice the equations to solidify your understanding. Great job, and see you in the next lecture. Thank you for joining us in week 3, and we look forward to seeing you in the next session. Have a great day.